we'll start with a simple example. Okay, so we're going to look at the temperature of coffee. We're going to find a formula for the temperature of the coffee. And the way to find a formula is to find how the temperature of the coffee changes over time. And there's two different coffees, the one at 30 degrees and there's one at 70 degrees, both at the same room temperature of 25 degrees. And the question is, which coffee will cool down faster? So the hotter one or the cooler one? The hotter one, right? Because it makes intuitive sense, because there's a bigger temperature difference, and it should cool down faster than the one with almost the same temperature, right? So we expect the coffee with 70 degrees coffee to cool down faster. Okay, so we need to describe this using derivative because it's a rate of change. So what we could do is we can let the temperature of the coffee be T and the E be the room temperature, which is a constant that doesn't change, whereas this one is a variable that changes over time. Okay, so what we could see at this point, that the rate of change of temperature, rate of change of temperature is proportional to the difference between the temperature of coffee and the room temperature. Okay, so this is a lot. Well, we can describe it using one equation. So the rate of change is dt dt. Right? It's proportional to means you're going to multiply by k times something times by the difference between the temperature and the room temperature. So that's the difference between temperature of the coffee and the room temperature. And because it's cooling down, the temperature is decreasing, we have a negative in front of K. Okay? So this is a way of describing the change. So this is what we call the Newton's law of cooling. Okay? So the Newton's law of cooling is a well-known example of natural decay. When a hot object is placed in a cool environment, the rate at which the temperature decreases is proportional to the difference between the temperature T of the object and the temperature of the environment, which is that, where K is a constant. And the solution to this is this. That's the solution to this. Okay, so you have an extra E there. So what you do is, and the same rule applies for heating it up, you just have a positive K instead of negative, and the same solution, except that's negative K, that's positive K. Okay, we're going to compare this with two-unit exponential growth and decay. So let's look at it briefly. So with the two-unit exponential growth and decay, is dq dt is equal to kq, isn't it? And the solution to that is q equal to a e to the power kt. This is 2-unit. And then in 3-unit, we have dq dt. Let's use the same pronumeral. We got k, but we have an extra pronumeral. We call it maybe e. So we got q minus e, like this. And then the formula for that will be q equal to e plus a e to the power kt. So you can compare and contrast the difference between the two formulas and the solutions. Okay. Okay, now be careful is that A is still the initial quantity. So Q equal to A when T equal to 0. When T equal to 0. Whereas this A is no longer the initial, because when you put T equal to 0, the initial quantity is actually E plus A. Okay, so there's a difference between that. Okay. All right, after we do this, we'll go to the next page. We'll do some examples. Okay. All right, so you don't have to memorize the formula. You just need to recognize this and know what to do with it when we were given a question on that. Okay, we'll do 2 examples, and then you can start the exercise. All right, we'll go to the next page. All finished? Good. All right, let's go to this bit. Example 1. We're going to look at the temperature of boiling water. Stanley takes a kettle of boiling water off the stove at time 0. So boiling water is 100 degrees Celsius. 5 minutes later, the temperature of the water is 70 degrees. It has cooled down a little. Show that this. So usually the question will give you a formula. You don't have to come up with that formula. They give you the formula and ask you to prove that it works for this. And it gives the correct temperature of 100 degrees, the boiling temperature at time 0. After that, find K. All right. So what we do is we first have to show that this thing works. This thing works to satisfy the differential equation. So what you do is you start with T equal to 20 plus AT e power negative KT. That's your first step. Just write down the formula. Once you write down the formula, is to differentiate it. dt over dt. Okay. Derivative of 20 is 0. Derivative of 80 is the second one, just 80 times negative k e to the power negative kt. Okay. Notice the first term becomes 0. And then what you do is you pull the negative k out. Just write negative k bracket at e to the power of negative kt. Okay. So pull the k out. And then you can see that I could write this as this. I could add an extra term. I'm going to add a 20 and subtract 20 at the same time. That will keep the expression balanced, like this. And then you see why I do this, because the reason why I added 20, because the 20 plus that is exactly equal to t. That's t. Which means I have to show that it works for this formula. Right? It works this. So it does satisfy the differential equation. Okay, so you have to show these steps. And it's going to be the same each time, so you do the same thing. Okay, so very often you get asked this question in the HSC exam in the 3-minute paper. After this, we're going to find that it gives the correct value of 100 at time equal to 0. So you substitute t equal to 0 and find out what time is. So you get 20 plus 80 e to the power negative k times 0. E to the power 0 is 1. And it does give you answer 100, as expected. Okay, so they ask you to check it at time 0. And also you have to find k. So we're going to work out what k is. Now k is that 5 minutes later, the temperature is 70 degrees. So when t equal to 5, the temperature becomes 70. And we have to solve for k. Okay, so let's do that. So we're going to solve for k. So we'll go 70 equal to 20 e to the power 80 e to the power of negative k times 5. Okay, and then we're going to solve for k. So this is extension 1. So you do have to do a bit more steps. So just subtract both sides by 20, which you will get 50 equal to 80 e to the power of negative 5k, like that. And then after that, divide by 80. So 50 over 80 equal to negative 5 e to the power negative 5k. And then you just ln both sides. So ln of this, notice I cancel the 0, equal to negative 5k. So k equals to negative 1/5 ln 5 over 8. Alright, use your calculator. And make sure you store that on a calculator. So we'll do ln 5 divided by 8 divided by 5 negative Okay, 0 point something, so maybe round to 3 significant figures. Negative 0.094, 0.0940. Okay. And you're going to store this on a calculator. You go Shift Store A. Alright, stores into A. Okay, which we'll use later on. Okay, any question? So it's pretty easy. Okay, so once we've got the formula, we can answer some question about the question. So we can find out how long it takes for the temperature to drop to 25 degrees. And then we can draw the graph of the function. Okay, let's do this question. So you have to find t equal to question mark when the temperature becomes 25 degrees. Okay, now we have a formula so we can work it out. So we're going to work out work out the time. So let's write down the formula first. T equal to 20 plus 80 is negative kT. And then we substitute 25 in and solve for the time. Okay, all right, do that. So you just do the same step as before when you find k. So subtract both sides by 20, you get 5, and then divide by 80, so you get 1 over 16. Remember you're finding t, so you get ln 1 over 16 equal to negative kt. Going back there, we get t equal to ln 1 over 16 divided by negative k. Use a calculator. So we do ln 1 divided by 16, close bracket, divide by negative a, like this. I've got k stored into a, equal 29.49. So you find how long it takes. So that's in minutes. So you can, yes, okay, that's in minutes. Okay, so we can convert that to 29 seconds. So about 30 seconds. So 29 minutes and 30 seconds. All right, 29 minutes and then about 30 seconds. Okay, so you can convert to that. Okay. All right, good. So now we'll draw the graph of the function. Okay. So let's look at the graph. So it starts off with 100 degrees. Okay, because it's cooling down. And then after 5 minutes becomes 70 degrees. That's the temperature. Oops. 70. That's the temperature. After 5 minutes. And then after a while, after about 30 minutes or 29 minutes, it's about 25 degrees. Okay, so you can connect the dots, you get this, right? Like that, okay? And then what you do is, for this graph, there's an asymptote as well. Like all exponential graph, they will have an asymptote, 20 plus 80 is negative kt. So to find the horizontal asymptote, you make t goes to infinity. So going back to here, we can write 20 plus 80, and then times by exponential, not shift that one, negative a, times, okay, we can substitute a big value after 100 minutes, after 1,000 minutes, it becomes 20, okay? So when t goes to infinity, temperature approaches 20 degrees, so that there's an asymptote. So therefore you can write that as that's 20 degrees, and then you can extend the graph as approaching 0, okay, approaching 20. And the graph is now drawn. Any questions? So how to draw this? Okay. All right, good. Now, why does it approach 20? Because it makes sense, because the temperature of the room is 20 degrees. So eventually, the temperature of the kettle must approach 20, isn't it? It can't just become 0 degree, it just froze for no reason, right? Okay? So it makes sense logically. All right, any question? All right, good. After this, we'll do one more question, then you can start the exercise. Example 2. All right, let's look at this. So, okay, a large French tapestry that are hung hung in the permanently air-conditioned La Chatelle Hall have a normal water temperature content of 8 kg. When the tapestries were removed for repair, they dry out in the workroom atmosphere. When they were returned, the rate of increase of water content was proportional to the difference from the normal 8 kg. That is this. They give you the equation for some constant K proportionality. To prove that for any constant, this is a solution to this equation. Okay, so like what we did before, we just have to prove that it works. Let's try to do that. So let's do dW dt equals to 0 minus a times negative k e to the power negative kt, like that. And then you can see the negative get cancelled. You get k a e to the power negative kt. So you take the k out. Now you have to be careful. You have to make it look like this. Make it look like this. So what you could do, you can put a minus in here, minus outside. So your next step will be negative k, negative a, e to the power negative kt. And then what you do is you add a k8 minus an 8. Does that work? Oh no, you have to. Oh, it works completely. Okay, all right. Which is equal to W. This thing is W. But of course, it looks different because we took the negative out. We shouldn't. Okay, but anyway, so we can put the negative in, so you get negative W plus 8, which become K 8 minus W, as we expected. Okay. Now, if you don't like to do it this way, there's another way you could do. Once you work out this step, once you work out the W dt is K A e to the power negative kt. I'm going to write down this is method 2. Once you get that, you can do the right hand side and left hand side separately. Okay, so let's do the right hand side. And the right hand side is, okay, the right hand side is K 8 minus W. And then replace W by, W is this, W is 8 minus A e to the power negative kt. And then you just expand 8k, 8 minus 8 plus A, which is equal to Ka. So you can do it on both sides. If you want to, you can do it that way. And then you can say, therefore, left-hand side equal to right-hand side. So you may prefer this approach. If the first one's a bit hard to see, you can prefer this approach. Okay? All right, I think that's it. Okay, good. Any questions? Okay, no question. Okay, let's move on to the next bit. Now we have to find A and K given these values. Okay, so let's find A first. So first we have to write down the formula, W equal to 8 minus A e to the power negative kt. And then we're going to substitute 4. So when t equal to 0, W equal to 4. Okay, like that. And then we're going to substitute 4 equal to 8 minus A e to the power of 0. What's e to the power of 0? 1. 4 equal to 8 minus A. And then A, 4 plus A is 8. So therefore A equal to 4. Okay, so find A first. And once you find A, you have to update your formula. So let's update the formula. So therefore, the formula now becomes W equal to 8 minus 4 e to the power negative kt. That. And then what you do is you substitute, replace W by 6.4. And then replace T by 3. Okay? So you get equal to 8 minus 4 e to the power of negative k times 3. And then we'll solve for k. So subtract both sides by 8 first. So you get minus 8 minus 8. That will be negative 1.6. and then divide by negative 4, so you get 0.4 equal to e to power negative 3k, and then ln both sides, ln 0.4 equal to negative 3k, therefore k equals to ln 0.4 over 3, negative 3, and then use your calculator. So you do ln 0.4, close bracket, divide by negative 3, you get 0.3054, 0.3054 dot dot dot, which you can store on a calculator. So you go shift RCLA, shift that, okay, which will be useful later on. Okay. Alright, so that's this. So we've got K and A. Okay, any questions? Alright, after this, we're going to find the rate of absorption of water after 3 days. Yeah, okay, good. So to answer this question, you have to find dW dt when t equals to 3. But the good thing is I know what the water content after 3 days is exactly 6.4. W is 6.4 from part B. So in that way, I could use this formula, dW dt equals to K 8 minus W. So to find out the water content, you just substitute 6.4 in here. So 6.4, 8 minus, times by the K, which is already stored on a calculator. So the alpha A times by 8 minus 6.4. 0.4886. So maybe round to the nearest 2 decimal place, so 0.49. So right, 0.49 kilogram, because the water content is measured in kilogram, per day. That's the rate of absorption. Okay. Or if you like, you can use the derivative formula, which is written before, K times AW. K times e to the power negative KT. Then you have to substitute t equal to 3 in here. So you go 3 K times, now A is what's A equal to 4? E to the power negative K times 3. You can also get the same answer. So let's try that. So you can do alpha A times by 4 times by exponential negative alpha negative alpha A times 3. Okay, so you get the same answer, 0.49. But this is harder, isn't it? 49 kg per day. So if you know the quantity, it's better to use this formula, dW dt equal to K times 8 minus W. Okay, after we do this, we'll do more questions. Go to the next page. Okay, find when does the water content has risen to 7.9 kilograms. So write down the formula again, like this. So you have to find t equal to question mark when W equal to 7.9. Okay, so you go 7.9 equal to 8 minus 4 e to the power negative KT. We're going to find out what t is. So we subtract both sides by 8, you get negative 0.1. And divide both sides by negative 4, you get 1 over 40. And then you ln both sides. Like that. And then you can do t equal to ln 1 over 40 over negative k. Okay, now sometimes the textbook may have a different answer in exact form, so they may do something like this, which is normal, so they can write that 1 over 40 as negative 1 over negative k, and the advantage of that is the negative will go down, that will cancel the k at the bottom, so they cancel the negative. So the answer, they could write that as ln 40 over k, okay? Alright, so now you have to work out the time, so you do have to use your calculator, do ln 40 close bracket divided by alpha A equal 12.077. 12.077, so approximately 12 days for it to reach 7.9 kilograms. 12 days. And then we can draw the graph. Okay, let's draw the graph. So let's use the information we got before. When T is 0, the water content is 4 kg, and after 3 days, the water content becomes 6.4, and then after 12 days, it's almost 8 kilograms, which is 7.9. So we can use this result to draw the graph, and then you get a few points, you get to see what the graph look like. Okay, so that's the time, that's the water content, that's 0. So it starts at 4 kilograms, and after 3 days, it becomes 6.4 kilograms. So that's in kg, that's in days. Okay, like that. And then you plot the points. Starts here and then goes here like this. Yep. And then we're going to continue. So like before, the asymptote is always the constant term. So if you look at the formula, W equals to 8 plus 8 minus 4 e to the power of negative kt. This number here is your asymptote. So you go 80 and draw a dotted line. Okay, and then you're going to draw this, and it's approaching this dotted line. Okay, that's it. Okay, so that's all done. Yeah. And of course, you can show more information, such as after 12 days, it's about 7.9 kilograms. Okay, after 12 days. All right, any questions? So pretty straightforward. You can start the exercise from the Maths in Focus textbook. Okay.